All right, welcome everybody. I want to take a look at some data that we're going to use to motivate our bootstrap distribution implementation that we use for loops for. So before we get into the bootstrapping, let's just talk about the sample that we're going to be working with. So we'll use some real data here. So let's say I'm a biologist. Work with golden jackals and I want to estimate what is the mean length of the jaw of all golden jackals. So mandible means jaw. So I want to come up with an estimate for the mean jaw length of all golden jackals. So I cannot go and find every golden jackal on this planet and measure their jaw length that has ever lived, right? So we don't have access to collect data from the full population of all golden jackals. So instead, what you would do is you would collect a sample. Hopefully, you try and collect that sample randomly so that it's not biased. And you collect some measurements from your sample. You look at the characteristics of your sample, and then you try and infer something about the population. So that's what we call statistical inference when we want to take properties from a sample and see what they tell us about properties of the population. So in this case, let's say our sample consists of 20 observations. So we collect a random sample of 20 golden jackals and we measure the length of their mandible for all 20 golden jackals. And this data is actually stored in a data set called Jackal. And in order to access that data set, it lives in a package called Permute. So if you haven't already installed a Permute package and loaded it, you'll want to uncomment out these two commands and run this code cell. I've already run them, so I've got the Permute package loaded. There is a data set called Jackal in that package that we're going to work with. So I'm going to run this code cell to load the Jackal data and take a look at a summary of what is inside of that. So it's a rather small data set. You can see we've got 20 observations in total, 10 male, 10 female jackals. And we can see there's really one variable there's two variables in the data set. One is the sex, and the other is the length of the mandible of that golden jackal in millimeters. There's only two variables in this data set, and there's 20 observations in our sample. So that's the data that we're working with. And in this code cell, I'm just using base R to create side-by-side box plots if we wanted to compare the distribution of mandible lengths for males and females. So there's certainly two subpopulations here that have different distributions of mandible lengths, but we're just going to group them all together, males and females, and just come up with an estimate for the mean length of the jaw for all golden jackals, male and female. Though I think it definitely would make sense to come up with two separate estimates, one for the male and one for the female. We're just going to give one estimate for both males and females. So our sample is going to be all of the length values, all of the values of the variable length in the Jackal data set. So I'm going to create a vector to store our sample. So my vector is going to be called jaw sample. So just recall that Jackal is a data frame that has two variables, so it has a different data structure. I'm going to extract the lengths and store them to jaw sample, and jaw sample is now a vector. So we've got a different data structure. So here are all 20 observations from our sample that is now stored in jaw sample. So now we've got our data set loaded up and ready to go. Let's say we want to answer the question, what is the average jaw length of all golden jackals? Well, we just picked one sample of 20 adult golden jackals that we've got stored. So we don't have access to the full population of all golden jackals. So if I've got one sample and I want to estimate the average mandible jaw length of all golden jackals, well, then it makes sense for me to think about, well, what is that characteristic for my sample? What is the mean jaw length of my sample of 20 golden jackals? And that's what I can calculate with mean jaw sample. And the mean of our sample is 111 millimeters. So if I were to, based on this one sample, if I were to give you my best guess for the average, the population mean, the average length of the jaw for all golden jackals, based on my sample of 20 that had a mean of 111, my guess would be, I think it's 111 millimeters. Makes sense that we would use the sample mean to approximate the population mean. But the problem here is if some other person went out and collected their own sample of 20 golden jackals, they would probably collect 20 different jackals than I had, and they're going to get a different sample mean from their sample. So my estimate of 111 is not certain to be true, right? Someone else picks a different sample, they're going to get a different estimate. So what we typically do when we're estimating the value of a population parameter is rather than give one value to estimate it, we give an interval estimate that's going to build in some margin of error into our estimate. So we'll say that I think the golden jackal jaw length is 111 millimeters plus or minus some margin of error. And one way to get that margin of error is to use the central limit theorem when we can and look at the distribution of sample statistics. And that's going to indicate how much variability we have in the statistic based on different samples. And so then we use kind of that spread of values in our sampling distribution to build in a margin of error into our estimate. And so in some cases, we do have a theoretical model, for example, using the central limit theorem to approximate the sampling distribution. There are other cases where we don't have a theoretical model for the sampling distribution. The central limit theorem doesn't apply. We can use bootstrapping in those instances. So bootstrapping is a really, really powerful way of approximating sampling distribution for any statistic, no matter how big our initial sample is. And that variability in our estimate does tie in to how much variability we have in our sample itself, the standard deviation of the sample. So if I have one sample of 20 golden jackals that has a mean of 111 millimeters, my first guess for the population mean would say it's about 111 millimeters. But what we need bootstrapping for is for us to put a numeric value on about, like how much variability should we build into our estimate. And that's where bootstrapping comes in. And so we'll pick up with that idea in the next video.